Here we're going to look at an interesting problem involving some means of binomial coefficients. And so let's recall what binomial coefficients are first. So in short, they are the building blocks of Pascal's triangle. So whenever you build Pascal's triangle, you start with a 1 here, 2 1s here, and then you keep doing 1s down these diagonals. And then you replace these numbers in the middle with the sum of the two above. So notice 1 plus 1 is 2. And then 2 plus 1 is 3, 2 plus 1 is 3, 3 plus 1 is 4, 3 plus 3 is 6, and then so on and so forth. All the way down to, this is happening down here as well, 21 plus 35 is 56. So it turns out that if you define a binomial coefficient by the symbol, we read this as n choose k, where the n's are going down and the k's are going across. So this is like 0 choose 0. Here we have 1 choose 0, 1 choose 1, 2 choose 0, 2 choose 1, and 2 choose 2, and so on and so forth. Then you can solve the recursion that's defined by this sum as it trickles down and get a nice closed form for binomial coefficients. So we're not going to prove this nice closed form in this video. Our goals are somewhat different. But what we get is that n choose k is equal to n factorial over k factorial times n minus k factorial. Okay, so now that we've got that taken care of, let's go ahead and look at what our goals are. So we've got two goals here. The first goal is to find the limit as n goes to infinity of the nth root of a sub n, where a sub n is the arithmetic mean of these binomial coefficients, n choose 0, n choose 1, up to n choose n. So that's like the nth row of Pascal's triangle. And then our second goal is this limit as n goes to infinity of the nth root of g sub n, where g sub n is the geometric mean of those binomial coefficients. Okay, great. So let's maybe get rid of this and then we'll start with our first goal. So now we're ready to start with our first goal, which is the limit as n goes to infinity of the nth root of the arithmetic mean of these binomial coefficients. So let's just go ahead and calculate this a sub n first. So notice this a sub n is going to be 1 over n plus 1 times n choose 0 plus n choose 1 plus all the way up to n choose n. Why is it 1 over n plus 1? Because there are n plus 1 terms here. Notice we're counting from 0 to n. That makes n plus 1 total terms. So now let's maybe go ahead and write this as 1 over n plus 1. And now we have this sum as k goes from 0 to n of n choose k. Now the next thing that I want to do is recognize this as some binomial that has been expanded and then evaluated at 1. So notice this is exactly the same as the sum as k goes from 0 to n of n choose k times x to the k, where we have evaluated x at 1. Because 1 to the k is just 1. But now notice that by another definition of binomial coefficients, which is somewhat well known, but we didn't talk about it before, we can take all of this and rewrite it as 1 plus x to the n. And then we are evaluating that at x equals 1. So in other words, we have 1 plus 1 to the n, that's 2 to the n over n plus 1. So let's see where we are so far. We have calculated the arithmetic mean of these binomial coefficients. It's 2 to the n over n plus 1. So that's a nice structure already. Now notice if we took the limit of this directly, we would get infinity because we've got this exponential thing in the numerator and then this polynomial type thing in the denominator. And so that actually provides some motivation for why we want to look at the nth root of a sub n, because that'll tame the growth of this so we can get some sort of maybe nice number out of it. So let's maybe go ahead and calculate this a sub n, the nth root. So that is going to be the nth root of 1 over n plus 1 times 2. So the nth root of 2 to the n is just 2, and then you get the nth root of the rest of this. Okay, great. So that now the next thing that I want to notice is that maybe it would be tricky to find the limit of this as n goes to infinity, but I can use a trick. I'm going to go ahead and rewrite this as 2 times e to the natural log of the nth root of 1 over n plus 1. So what fact did I use right here? I just used the fact that e to the natural log of u is equal to u, and that's going to be true for all like appropriately chosen u. But now we've got a natural log, and we can use some natural log rules to simplify this. So remembering that this nth root of 1 over n plus 1 is the same thing as 1 over n plus 1 to the 1 over n. We can rewrite this as 2 and then e to the minus 1 over n natural log of n plus 1. So notice I took n plus 1 out of the denominator by putting a minus sign out front, and then I changed this exponent of 1 over n to a multiplier of 1 over n by bringing it outside of the natural log. Okay, great. So the next thing that we want to do is finish this off by calculating this limit. So now this limit as n approaches infinity of the nth root of a sub n, so that's going to be equal to 2 times the limit as n approaches infinity of e to the minus 1 over n natural log of n plus 1, like that. But now we know that the exponential function is a continuous function. So we can bring that limit inside of the continuous function. That gives us 2 and then e to the limit as n approaches infinity. Maybe we'll take this minus sign out, and now we have natural log of n plus 1 over n. Great. But now notice we've got an indeterminate form. As n approaches infinity, the numerator approaches infinity and the denominator approaches infinity. So that means we can apply L'Hopital's rule to this thing that's happening in the exponent. That's going to give us minus the limit as n goes to infinity of 1 over n plus 1 over 1. So that's the derivative of the natural log of n plus 1 divided by the derivative of n. But now we can see as n goes to infinity, this part goes to 0. And so we're left with 2 times e to the 0, but e to the 0 is 1, so we're left with 2. So we found a solution to our first goal. This limit of the nth root of the arithmetic mean of these binomial coefficients is equal to 2. Okay, let's go ahead and clean this up, and we'll look at our second goal. Now we're ready to look at our second goal, which is the limit as n goes to infinity of the nth root of the geometric mean. So in order to do this, I'm going to introduce a new sequence, and I'll call that sequence p sub n. So let's maybe set p sub n equal to the product of these binomial coefficients. So in other words, it's the product as k goes from 0 to n of n choose k. You might say, well, why do I want to do that? Well, it'll be useful to work with this instead of g sub n for much of our calculation. Maybe let's go ahead and notice over here that g sub n is going to be equal to the n plus first root of p sub n, just by the definition of the geometric mean. We're multiplying together n plus 1 terms, so that means we need to take the n plus first root. Great. But then furthermore, that tells us that our goal, which is the nth root of g sub n, is really p sub n to the power of 1 over n times n plus 1. We're taking an nth root from this part in the formula right here, and then we're taking an n plus first root from the fact that we've got a geometric mean. Great. So let's maybe put a box around that. We have kind of rewritten our goal in terms of this p sub n sequence. The first thing that I want to do is simplify this a little bit by starting the product at k equals 1 instead of k equals 0. And we can actually do that without changing anything because n choose 0 is 1. So effectively what we're doing is just dividing out a 1, but that's not going to change anything. Okay, great. And now what we want to notice is that we can rewrite this with our formula for binomial coefficients as the sum at the product as k goes from 1 to n of n factorial over k factorial times n minus k factorial. Good. But then expanding this out, let's see what we get. So we're going to get n factorial over 1 factorial, n minus 1 factorial. So that would be like the k equals 1 term. And then next, we're going to get n factorial over 2 factorial times n minus 2 factorial. So that would be like the k equals 2 term. Next is going to be n factorial over 3 factorial, n minus 3 factorial, all the way up to, but there's some symmetry in the binomial coefficients that you might have seen in the Pascal's triangle. This is going to end the same way that it started, just in reverse. So we'll have n factorial over n minus 2 factorial times 2 factorial. So that would be like the k equals n minus 2 part. And then we've got n factorial over n minus 1 factorial times 1 factorial, and then finally n factorial over n factorial times 0 factorial. And then again, we might as well not worry about this one, because this one is also equal to 1. Now let's start rewriting this a little bit. So notice the numerator is going to be n minus 1 copies of n factorial. So we can write that numerator as n factorial to the power of n minus 1. Now let's go ahead and reorder the denominator so the like terms are next to each other. So notice we're going to have 1 factorial squared, 2 factorial squared, 3 factorial squared, all the way up to n minus 1 factorial squared. So that's just from reordering this 1 factorial next to this 1 factorial, this n minus 1 factorial next to this n minus 1 factorial, and so on and so forth. Now the next thing that I want to do is simplify this denominator a little bit more, or maybe I should say rewrite this denominator. It's questionable if this is simplification or not, but it will help us towards our goal. So I want to write these as like terms in the denominator. So let's see how I can do that. So I've got an n factorial to the n minus 1 in the numerator. And then in the denominator, I have a 1 raised to the 2n minus 2. And so why is it 2n minus 2? Well, we get a 1 squared from here, a 1 squared from here, a 1 squared from here, all the way up to there. So 1 to the 2n minus 2. Great. And now, how many 2's do we have? Well, we get a 2 squared from here, a 2 squared from there, and so on and so forth. But we do not get a 2 squared from here. So that's going to be 2 to the 2n minus 4. Similarly, we're going to have a 3 to the 2n minus 6, all the way up to this n minus 1 will be raised just to the second power. So n minus 1 will just be squared. So we've got it broken down to this. Okay, now maybe I'll go ahead and bring that up and then we'll move on to the next step. So on the last board, we wrote this product of binomial coefficients in the following form. So we've got this n factorial to the n minus 1 over 1 to the 2n minus 2, 2 to the 2n minus 4, and so on and so forth, all the way down to n minus 1 squared. So now what I want to do is apply the natural log to this to kind of tame these exponents and this big division and stuff. So let's go ahead and do that. So I'll take the natural log of p sub n, and notice that that is going to give me the natural log of the numerator, which is n factorial to the n minus 1, minus the natural log of the denominator, which is all of this stuff. So I'll have 1 to the 2n minus 2, 2 to the 2n minus 4, all the way down to n minus 1 squared. Now let's apply some more natural log rules here. So I can rewrite this as n minus 1 times the natural log of n factorial. And then this is going to be minus, now I'm going to put a big brackets here, and we're going to have the natural, we're going to have 2n minus 2 times the natural log of 1. And you might say, well, I know that the natural log of 1 is 0, but we're going to leave it in there just so that we have some structure. And then it's going to be plus 2n minus 4 times the natural log of 2, plus all the way down to 2 times the natural log of n minus 1. Now next what I want to do is similarly break up this n factorial. So we know n factorial is n times n minus 1 and so on and so forth. So we can use the natural log to break that up into a sum. So that's going to give us n minus 1 times the natural log of 1 plus the natural log of 2 all the way up to the natural log of n, like that. Great, and now we have to subtract all of this off. So we're subtracting off 2n minus 2 times the natural log of 1 plus 2n minus 4 times the natural log of 2 all the way up to 2 times the natural log of n minus 1. Now what I want to do is go ahead and combine like terms here. So notice I can combine a natural log of 1 here with the natural log of 1 here. Keeping in mind I've got my coefficients. And then my natural log of 2 here can combine with the natural log of 2 here, and then so on and so forth. So notice everything from this first bit is connected to an n minus 1 as a multiplier, but these are connected to all sorts of different other things as multipliers. Okay, so let's go ahead and see what we get here. So what do we have in front of the natural log of 1? So in front of the natural log of 1, we're going to have n minus 1 minus 2n minus 2. So we'll leave it like that for now, but we'll probably simplify that in the next step. Then next, what do we have in front of the natural log of 2? So we're going to have n minus 1 minus 2n minus 4. So that's going to be times natural log of 2. Let's go ahead and write natural log of 3 in here. So that's going to be plus n minus 1 minus 2n minus 6 times natural log of 3. And then let's see, for the n minus 1, the natural log of n minus 1, we're going to have n minus 1 minus 2. So that's going to be plus n minus 1 minus 2 times the natural log of n minus 1. And then finally, plus n minus 1 times the natural log of n. So let's see here, we have n minus n, so that's going to give us minus n, negative 1 minus negative 2, so that's going to give us a positive 1. So this part right here simplifies to 1 minus n. Great. Now let's see what this part simplifies to. So again, we're going to have a minus n, but now we have minus 1 minus negative 4, so that's going to be 3 minus n. And then similarly, this next one is going to simplify to 5 minus n. Great. And then notice over here, this simplifies down to n minus 3. So now let's see how we can maybe put all of this together into one sum. So now this is going to be the sum as m goes from 1 to n, and then the natural log of m, like that. Now we just have to figure out what this coefficient of the natural log of m is in terms of this kind of setup right here. So notice it increases by 2 at each step, but it starts with 1. So I think we can do that by doing 2m minus 1 minus n. So let's go ahead and check to see if that works. If we set m equal to 1, we're gonna have 2 minus 1, which is 1. Good. If we set m equal to 2, we're going to have 4 minus 1, which is 3. N equal to 3, 6 minus 1, which is equal to 5. Okay, great. And now let's see if it works down here. So m equals n minus 1. So if m is equal to n minus 1, then yeah, that is going to simplify down to n minus 3. So this all checks out. Okay, so now we've got a closed form for the natural log of this product. Let's maybe go ahead and bring that up and we'll move on to the next step. So on the last board, we ended at the following point. So we've got the natural log of this product is equal to the sum as m goes from 1 to n of 2m minus n minus 1 times the natural log of m. Now we're going to do something that's a little bit tricky. We're going to add and subtract a term. And what term are we going to add and subtract? It will be n times the natural log of n. So let's go ahead and do that. Let's do minus n times the natural log of n plus n times the natural log of n. So clearly that doesn't change anything because that's equal to 0. Now the next thing that we want to do is write this n in a particularly tricky way. And this tricky way will allow it to be absorbed into this sum up here. So I want to write this in the following tricky way. So that's the same thing as n times n plus 1 minus n squared. Great. So that makes sense because we've got n times n is n squared minus n squared, so we're good to go. But the important thing to notice here is that this is twice a triangular number. In other words, this is 2 times the sum as m goes from 1 to n of m. So that's how we get some of the simplification in there. And then the next thing that I want to notice is I can take this n squared and rewrite it in a tricky way as well. I can rewrite that as the sum as m goes from 1 to n of n. So if I add n to itself n times, that's the same thing as multiplying n to itself, which gives us n squared. So in other words, this term, which is minus n times the natural log of n, can be rewritten with both of these parts. So let's maybe go ahead and write that down. So that's going to be the natural log of n times this sum as m goes from 1 to n of 2m minus n. Great. But notice we've got a 2m minus n in here, and so that's lucky. We want to combine this guy with the 2m minus n that's in the sum that we already have. So let's maybe go ahead and do that. So we've got this is now equal to the sum as m goes from 1 to n of 2m minus n times the natural log of m minus the natural log of n. So that's from absorbing this red thing inside of here. Good. And now next, I'm going to break off this minus 1 times the natural log of m and put it outside. So that's going to be minus this sum as m goes from 1 to n of the natural log of m. Great. And then finally, I have this leftover term, which was used so that we could subtract that n natural log of n, and that's going to give us plus n natural log of n. Great. So now maybe I want to combine this stuff together using some log rules. So I can rewrite this as the natural log of m over n. So that allows me to rewrite all of this as the sum m goes from 1 to n of 2m minus n times the natural log of m over n, again using log rules. And then I can just go ahead and bring this down. So that's going to be plus n times natural log of n minus the sum m goes from 1 to n of the natural log of m. So I just reordered that a little bit. Okay, so now we've got a nicer closed formula for this natural log of p sub n. I'll go ahead and bring that up and then we'll keep going. So we're moving towards the end. We've got the natural log of p sub n is equal to this object that I created on the last board. And then earlier on in the game, we said that our goal was really to find this limit of p sub n to the 1 over n times n plus 1. Well, we don't have p sub n by itself, but we do have its natural log in a form which is not so hard to deal with. So if we can find the natural log of the limit, then we can also find the limit. So just to reiterate, what we're actually finding at this juncture is the limit as n goes to infinity of the natural log of the nth root of g sub n, where that is our geometric mean again. Okay, good. So now notice that's going to be the same thing as the limit as n approaches infinity of the natural log of p sub n to the power 1 over n plus 1 by our earlier discussion over there, which is in that box. Now I want to use a natural log rule to simplify that a little bit. So that is going to be the limit as n approaches infinity of 1 over n times n plus 1 times the natural log of p sub n. But what I want to do is rewrite the natural log of p sub n as what we have up here. So that's going to be this sum m equals 1 to n of 2 to the 2m minus n natural log of m over n, and then plus n natural log of n minus the sum m equals 1 to n of the natural log of m. Great. So now I want to do something that's a little bit tricky, but it's not too hard to prove from like a real analysis class. And that is if I replace this 1 over n times n plus 1 with 1 over n squared, I will get the same limit. So that's exactly what we're going to do here. So replace this with n squared in the denominator instead of n plus 1 in the denominator. Okay. So that's going to allow us to rewrite this in a way which is a little bit easier to work with. So we've got this limit as n goes to infinity. Now what I want to do is take this 1 over n squared and distribute it through to all of these parts. So let's see what I get. I'm gonna have 1 over n, and then this sum, m equals 1 to n of 2 times m over n minus 1. So that's what I get from taking one of the 1 over n's and putting it out front of the sum, and the other 1 over n and bringing it inside the sum and distributing. So that gives me 2m over n minus 1. And now I have the natural log of m over n. Great. Now bringing the 1 over n squared to the next parts, we get plus, and then we'll have the natural log of n over n. So notice we've got n over n squared is going to give us 1 over n, and then minus 1 over n squared times the sum, m goes from 1 to n of the natural log of m. Great. And then we can go ahead and close these parentheses off. Now I want to quickly take care of this stuff that I'm going to box in yellow, because as we'll see, it will not contribute to the limit. So let's take that stuff in yellow and maybe take its absolute value. So the natural log of n over n minus 1 over n squared times the sum, m goes from 1 to n of the natural log of m. So notice that is going to be less than or equal to the natural log of n over n plus the sum, m goes from 1 to n of the natural log of n, and that's times 1 over n squared. So let's see, I took the absolute value of both parts using the triangle inequality. And then next, I replaced this natural log of m term with the natural log of n. That's the largest value that m can take, and thus I created something larger. But now here I'm adding n copies of the natural log of n together, which means all of this adds up to n over n squared times the natural log of n. So in other words, we have all of this stuff adding up to 2 natural log of n over n. And that approaches 0 by L'Hopital's rule. That's pretty similar to one that we saw earlier. So that means all of this stuff in the yellow box approaches 0, which means we don't need to consider it in this limit. Okay, so maybe I'm gonna go ahead and erase this line and then we'll finish it off. So we just got done showing that that yellow boxed stuff goes to 0, and now we're ready for one of my favorite tricks. So we wanna be inspired from something from Calculus 1 or Calculus 2 to simplify this remaining sum. So I wanna notice that if I set delta x equal to 1 over n, and then I set x sub m equal to m over n, then this looks like the Riemann sum of the integral of a certain function. And so notice that this looks like f evaluated at x sub m, and then out here is this delta x. But what would that function be? Well, we have 2x minus 1 times the natural log of x. So in other words, after taking the limit, this becomes the integral from 0 to 1 of 2x minus 1 times natural log of x dx, which I think is pretty nice. So now all we have to do is calculate this integral. How can we calculate this integral? Well, probably with integration by parts, given that we have some sort of inverse function here. So I'm going to go ahead and let this part be equal to u, and then all of the rest of this will be equal to dv. And then the integration by parts formula says that you're going to do u times v, so that will be x squared minus x times the natural log of x, evaluated from 0 to 1, minus the integral of v du. So let's see, that's going to be minus the integral from 0 to 1 of v, which is that x squared minus x, times du, but that's going to be 1 over x, so that's going to be x minus 1 dx. So something like that. Great. But now what we want to notice is if we plug 1 into this, we get 0. If we plug 0 into this, well, it's an indeterminate form because of the natural log, but it will approach 0. You can calculate that with a limit. And we're just left with this thing over here. So notice the antiderivative here will give us x minus 1/2 x squared, evaluated from 0 to 1. I switched the order there just to absorb the minus sign. But now notice that is going to simplify down to 1/2. So we've got a value for this limit of the natural log of the nth root of the geometric mean. So that's equal to 1/2. Now we're essentially ready to finish it off. So after a bunch of work on the last board, we finished with the following limit. So we've got this limit as n goes to infinity of the natural log of the nth root of g sub n. In other words, that geometric mean is equal to 1/2. Now we're going to use the fact that natural log is continuous to bring the natural log out of this. So we have the natural log of the limit as n goes to infinity of the nth root of g sub n equals 1/2. And now we can exponentiate both sides to get our goal, which is that limit. So we exponentiate both sides and we have the limit as n goes to infinity of the nth root of g sub n is equal to e to the 1/2, which was our second goal. So we've got this value for this second limit is equal to the square root of e. And that's a good place to stop.